We have been looking at the search problem for the last few videos. In fact, we have come a long way. We started with linear search, then we went on to look for jump search in sorted lists, and then we looked at binary search, again for sorted lists. Now, all of this we have looked at in a lot of detail, looking at the different cases, analyzing how the algorithm works, and so on. It's now time to put it all together and do a sort of comparison between, say, linear search, binary search, and jump search with respect to their complexity. This is quite interesting because that kind of illustrates in a nice way the comparison between them, and the message that comes out is really unmistakable. So to do it all, in a, let's say, understandable manner, we are going to create an experiment. So we are creating a list of all numbers between 0 and, let's say, approximately a million. So this list is a million long. Now we run a loop through this. So basically we select a value at random, which is always in the list. And then we keep monitoring how long does it take to search this, let's say with linear search, binary search, and jump search. And for jump search, we use square root n as a size because, as we have seen, that's optimal. That makes it, let's say, root of n scaling in terms of complexity, right? So a few things to be kept in mind. Number one, this list we are looking at is fundamentally sorted. Number two is that, this, remember, was linear scaling. This was logarithmic scaling. This is square root scaling. So we'll see how all of this compares. So like I said, we are basically creating an experiment. I do 100 attempts of this. I create a list, and then I just randomly pick up an item. Pick up an item randomly, basically random dot choice, and then see how long it takes to search with linear search, jump search, and binary search, and I log the time that it takes. Now, having, let's say, log this time, we are going to visualize this by plotting it. And for this purpose, I use two very popular libraries, matplotlib and numpy. Basically, these are scientific computing libraries available in Python, which help us to visualize data. So what I'm going to do is to plot, let's say, the value that I'm searching, on the x-axis, and the time taken on the y-axis for linear, let's say, linear, binary, and jump search, right? So when I do this, very interesting insights start coming out. You notice that, it first look clearly linear search, which is the red color, starts to be like, the most time consuming thing. And few things to be noted here. Number one, notice linear search, it's obviously taking long time because scales within. Also, the time taken to search increases as I go further into the list, and that's the nature of linear search. Exhaustive, we are looking at every item, so obviously the deeper it is, the deeper the item is in the list, the longer it takes, and that's exactly what we are seeing here. From the first look, it looks like, look, jump search and binary search are about the same, but we'll see a more clearer picture when we zoom into that. Now, as you know, we have spoken about this before. Time taken is not a precise metric, which is why sometimes you have outliers. We can ignore them. If you really, really want a very precise measurement here, we could look at, let's say, the number of iterations that we ran. So we can enhance the function to return, let's say, the count of iterations that has been run, and then that may make an interesting exercise itself. Yeah. But like I said, this two look like they're almost the same, but the picture will change once we zoom into this, because basically this is significantly more than this. So, we're not able to see the trend clearly. But let's say I go and zoom in only to those, let's say, a smaller amount. So again, x-axis is the value being searched, y-axis the time taken to search. You notice that linear search is literally going through the roof. That was linear scaling, remember. Now I see that binary search is almost close to zero, whereas jump search, I see a bigger spread, and also I see that increasing trend. Now, what is the reason for this? Remember, binary search, the number of iterations is always very small, logarithmic. Also, given that the value to search, it really doesn't matter much where I'm searching. Okay? On the other hand, with jump search, remember, with square root n, the scaling is square root n. So which means as I go farther and farther into the list, I am having to do more work, and this is scaling by square root of n. So clearly you see that binary search is winning here. Jump search comes next, and linear search is way more expensive with respect to computation. So there are two messages I would like you to take from here. Number one, specifically for search, whenever you have a sorted data, binary search is the way to go, because as you are seeing here, compared to jump search, in fact, binary search is much, much, much more efficient. Linear search for a sorted array really doesn't make sense. Now, this is important because you will realize that there are many search problems in which, immediately doesn't look like binary search is useful, but in fact, binary search is useful. And that's where we're going to go next. We'll see how binary search should be used to efficiently solve those problems. That's a topic we're going to pick up next, in the subsequent videos. But, the second message is a bit, let's say, broader. You remember we started with linear search, which is linear complexity, jump search, which was square root complexity. binary search, which was logarithmic complexity. So what this is also telling you is that, look, if you have an algorithm that is working in linear time, which is basically scaling as n, for example, well, try to make it better. And making it better could be, for example, in this case, going from n to square root, and that is going to be a significant improvement. However, if you have something in square root of n, well, think further and see if you can go to logarithm of n, because if you get into logarithmic complexity, it is really much smaller than square root. So that's the broader trend here. Later on, we'll also look at algorithms which will run in n square times. From there, coming to n itself will be big, but then, if you can go further down, that will be really nice. Yeah. Obviously, problem has to be solved correctly. So, that cannot be compromised. Not every algorithm can be made logarithmic, but in this case, in search, definitely it can be. And hence, we are going to go towards binary search in a very strong manner. I hope this journey has been interesting to you. Do reflect on it. We have covered this in a lot of detail, the concept, the intuition, as well as the nuances of the code. Think through them carefully. Very happy to discuss and enjoy programming. Do look at our website www.ybyte.in, because we have a lot of such content from which you can learn programming. Take care. Thank you so much. Bye bye.